Hello, everyone. I'm Samuel Dooley, and in this talk, I'm going to discuss my collaborators and my work, which finds that classification models on common datasets using common neural networks can systematically put certain types of data more at risk to misclassification. In traditional systems, which attempt to measure the fairness of a classification algorithm, we tend to think about the output of that system, saying things like these points are classified in this way, or the result of this classification in society was this. But this output-based notion of fairness often centers discussions and questions of identifying instances of unequal treatment of groups by the one-shot final result of the system. But in our work, I'll show you how this output-based view can miss certain types of unfair treatment. Specifically, I want to focus on what happens to points if there is noise or perturbations in your classification system. From a fairness perspective, this opens an interesting question. What if some points are systematically more robust than others? Put another way, for a data set, are there groups of points which are generally closer to or further away from the decision boundary? And if so, why would this be happening? To show you what I mean by all this, let's take a system with 2 points, a circle and an X, both of which are correctly classified. Now, if there was some noise in the system, what would happen? Noise is a reasonable assumption in many settings. For instance, if you're using a sensor to observe data, like a camera, and that data is transmitted with noise, or you might perceive that there's some adversary that manipulates your data. In these instances, the noise would move the data around in your input space, and perhaps that data would hop across the decision boundary and be misclassified by the system. This is obviously can be a problem, and we generally want to avoid this. One immediate observation about this type of threat is that points that are closer to the decision boundary are more susceptible to this sort of mistreatment, and points that are further away are more robust to misclassification. Um, to answer the main question about whether some groups of points are systematically more robust than others, that's the main part of our work, and I'll give you a sneak peek that the answer is yes. In our work, we find that on common data sets and on common models, some groups of points are just across the board closer to decision boundaries and more vulnerable to these sorts of misclassification problems. And in this talk, I'm going to formalize that notion of what we call robustness bias, provide methods to efficiently estimate it, and I'll demonstrate that this bias exists in the wild and how much that depends on the model and how much depends on the data set. Now, before we get started, let's talk about some data preliminaries and some terminology that we'll use, particularly partition. A data set generally can be partitioned or split into different groups. There, you might have a data set that can be partitioned based off of the predictor variable, in this case, a red and a blue class. You might also have that same data set might be able to be split or partitioned into groups by a sensitive attribute, in this case, a circle and X's. And you might be able to represent the entirety of those two partitions in this one unified data set with red and blue circles and red and blue X's. But I will discuss partitions to define the way in which we can split the data, often based off of a predictor variable or a partition based off of a sensitive attribute. To expand a little bit some more, let's build some intuition about this robustness bias problem. So recall that we're concerned about a noisy sensor and some adversary or an adversary that manipulates your data. And let's assume that these data have some decision boundary that runs through them. Again, if we have some noise, that noise would move your data points around in your space, and some might cross the boundary. And in this case, 9 of your points would be misclassified, and this would obviously be a problem. In our work, we're going to be primarily concerned with the treatment of how the different groups, the different X's and O's and circles and blues and reds are treated, and whether that treatment is different across those different groups. So returning to our original data, given a trained model and a decision boundary, if we're interested in the differing treatment of these different groups, we might assume that there's some threat model that might be able to alter our points by some tau bit of noise, and we can run that tau throughout our data, and we can calculate the proportion of our points that are within that tau. And this is where partitions are very useful, because we can then look at both partitions, and we can look at whether they're equally treated. And so in this case, in the predictor attribute partition, there's equal treatment. Both red and blue are two-thirds of those points are within tau. And that's also the case in this instance of the sensitive attribute. Two-thirds of the x's and two-thirds of the circles. But that obviously wouldn't always necessarily be the case. Consider the same data with a different model, again with the same tau. In this case, there is some different treatment. In the predictor partition, that's not the case, and we don't have that. There's equal treatment. A half of the red and half of the blue are within tau, but there is differing treatment of the sensitive partition. In this case, the x's are only 1/3 of the x's are within tau of the decision boundary, but 2/3 of the circles are. And this disparity is what we term as robustness bias. And it's easy and natural to see that this can depend on the data, on the model, and on the partition. And it's also equally easy to see that it would depend on tau as well, where tau here could be any number of things. And so let's look a bit more at how that tau might be chosen, and some ways to unify these different competing things that robustness bias might depend on. So we'll define some metrics. So first, you're given some data set. In this instance, you're given a data set of 3 partitions, blue, yellow, and brown, where the brown points it's easy to observe, they're just generally closer to the decision boundary. Let d theta be the function which gives the minimal distance of a point to the decision boundary for a model that's parameterized by theta. And for the time being, let's just assume that you can evaluate that function. It's exact and computable. We then can define this function I hat sub p, which takes as input a distance tau and a partition p, right? The numerator calculates the number of correctly classified points in p, which are at least tau away from the decision boundary. So in essence, this is computing the proportion of correctly classified points in a partition. That also is at least tau away from the decision boundary. We're only going to consider correctly classified points because we want to measure like the likelihood that some noise or some perturbation would decrease the performance of the model. Note that this is a function over tau. And so when tau is 0, the numerator would be all the points in the function would evaluate to 1. When tau is infinite, then the function would evaluate to 1 because all the points, when tau is infinite, the function would evaluate to 0. Since the brown points are closer to the boundary, this would mean that for a given tau, we expect it to we would expect that this function value to be smaller than the other two classes, and that's exactly what we see here. We see that the curve for the brown class is below the curve for the yellow and the blue class. But this measure is a function over tau, and it's generally better just to have one number. And so we can improve upon this by looking at the area under the curves, which is equivalent to the average distance to the boundary for a given partition. We do this by calculating the relative difference for the area under the curves, and we call this thing sigma. And the value of sigma for a partition will be this unifying measure about the relative robustness of that partition for the given data set and model. Sigma would happen to be negative if it is more vulnerable or less robust, and we can represent it on this color graph as being red, and so that's why the brown partition has this red color next to it, and sigma would be positive, and when your partition is less vulnerable or more robust, and so the yellow and blue are lighter shades, and yellow is blue because it's the most robust, right? So this takes us to our main research questions. And so how did we set up our experiments and all? Well, our two main research questions are, first, like, does this phenomenon, which we hypothesize to exist, does it exist in the wild? And to answer this question, we use the previously discussed metrics, and if we were to run it on, if we were to evaluate like sigma on different models and data sets, would sigma be significantly high or low? And then that would tell us if there's robustness bias. But to what extent is that sigma just by chance, or how much does it depend on the data set and model? And that's our second question. How much does the presence of robustness bias depend on the data set, the partition, and the model, and the combinations thereof? To answer these questions, we used the experiments for the CFAR 10 dataset and the CFAR 100 dataset, as well as CFAR 100 super class, which is just 20 classes of the CFAR 100. We also used AENS and UTK face datasets. As for the partitions that are available for these datasets, obviously they all have the standard predictor variables just based off their class. And for the CFAR datasets, that's their image class labels. And for AENS and UTK face, that class is the age category. Additionally, with AENS and UTK face, we can analyze partitions over gender, and with AENS, with UTK face, we can do that over a race partition as well. And I want to note here, obviously, that the use of these face data sets and the categorization of unwitting individuals into a category across gender, racial identities, just by the presentation, their presentation in a single image, like that's not great. That's there are lots of problems with that. We use these data sets and these partitions, though, to sort of audit their use and highlight the disparities with the robustness bias measure. As for the models, we performed evaluations with these models here, common neural networks that have been used for a while and are somewhat standard at this point, and also like vision. These are all vision data sets, and so these are vision models as well, so convolutional models. For each one of these model data set pairs, we trained the models by fine-tuning ImageNet features. We did this because we're mostly motivated by common real-world applications. And this is a reasonable assumption of like what one might naively do if they wanted to train a particular model on a data set. We also trained classifiers from scratch as well without pre-trained weights to test the pre-training's impact. After training these models on the different data sets, we evaluated their performance, just overall accuracy performance, as well as computing the I sub p curves and sigma as well, and looked for evidence of robustness bias. Now, on those models that I just described there, we can't exactly compute d theta of a particular image. There's no closed form solution to do this, and this is really an open area of research in the ML research community. But there are at this point there are two common ways of approximating d theta. One provides an upper bound, and the other provides a lower bound. And to compute an upper bound on d theta, we use something that's called an adversarial attack. And what this method does is it takes a model and a particular input image, and it alters that image in small ways, creating small little perturbations until that altered image is misclassified by the model. And once that altered image is misclassified, you can then look at the distance between the original image and the altered image, and that provides an upper bound. There are many different types of adversarial attacks, but the two that we chose to evaluate or use as ways of estimating d theta were Dietful and Carlini-Wagner. To compute a lower bound, you can do this by taking the same data, and for each data point, you can assume that there exists some compact region around that data point, for which every point in that compact region has the same class and the same class of the original point. And if you were to able to come up with the radius for that point, the radius for that compact region, that would be a lower bound. And this is called randomized smoothing. So these three methods are all ways in which we use to estimate d theta, and we'll present results for those all of those methods now. So first, we're going to look at the UTK face results. All of the results are in the paper, and we'll just talk about a few interesting facts here. So in the middle, we show that the hat IP curves for one model, DenseNet in particular, over the race partition, and this is the deep fool evaluation method. We see here that there's a clear order to these curves across all values of tau. And that order goes from top to bottom of Asian, other, white, Indian, black. It goes across all of the taus, and it's a clear ordering. Interestingly, we see that at a tau of just a half or 0.5, 90% of the black group is vulnerable or within 0.5. While only 60% of the Asian group is vulnerable. When we look at the color graph, we see that this behavior is pretty stable across the different models. Recall that this is reporting sigma, which, if you remember, is the relative area under the curves. And a red color means that the partition is more vulnerable, or that the curve is lower, and blue means that it's less vulnerable. Moving horizontally, you have the different partitions. In this instance, it's white, black, Asian, Indian, other is the order from left to right. And then moving vertically, moving down, you have the different types of models. And we see that across all of the models, the black and Indian partitions are red, meaning that they're more vulnerable, whereas the Asian and other partitions are less vulnerable. And this behavior is also similar across all of the measurement techniques as well. Deep fool, Carlini-Wagner, and randomized smoothing all have a very, very similar behavior. And then when we look at the other partitions for UTK face, age and gender, we see two things. One, that these partitions also have robustness bias to varying degrees. And also, two, that there's strong agreement across the measurement methods with the bias that we exhibit or that we observe. Now we can look a bit at the Adians data set, and we see very similar trends. The curves in the middle show the gender partition on the Adians data set, again for deep fool. We see that there is a more equal treatment between the male and female groups, and also that for small taus, the male group is a little more vulnerable to perturbation than the female group. Again, over in the color graphs, we see a similar behavior for the gender partition, which is about equally robust. And you'll note at the top that some of the models, as evaluated by the upper bound method deep fool, do flip the order of male and female, but it's not significant. They're very, very similar. As for the broader class the broader general class partition of the Adians data set, we again see strong evidence of robustness. And in this instance, the middle group is very blue, meaning that it's more robust across all the models and all the measurement techniques. And this dominant group means that the other groups of this partition generally are more red and more vulnerable to attack. We see that there is some disagreement across the data set for UTK face about the color sometimes slips and so, but generally it is there's very strong agreement. And these results, I think, are interesting, very surprising in some illuminating ways. Primarily, it shows that robustness bias does exist and can be stable across different methods of estimating it, stable across different models as well. When you run a Pearson chi-squared test on the agreement of deep fool and Carlini-Wagner, the upper bound methods, you get very, very strong agreement there. And there's, to some lesser extent, you see, but still there's agreement between the upper and lower bound approximation methods. Next, I'll talk a bit about mitigating it because that's an important step. Finding a way to sort of fix this is obviously a really important question. We tried the obvious regularizer approach where we add this regularizer, which computes the absolute difference in the proportion between the two, between a particular partition, adding this value to the optimization objective, then sort of penalizes if there's a robustness bias. We implemented this technique and have been able to show that the disparities in robustness bias does get better. But on the whole, it does seem to just move everything. The general overall treatment of the robustness tends to get worse. So so balancing those two will be a priority in future work. There's ways in which you can perhaps try adversarial training to sort of try to do both of those things at the same time. It would also be really interesting to like actually try this in deployed models, like do some more work of auditing deployed models. It would be really cool to understand more deeply what's going on here. It's a very, very interesting phenomenon. So there's a lot of work that can be done here. Me and my collaborators are really interested and excited about this line of work. We would love to engage with you and hear what your thoughts are. Our emails are there. Please reach out. This QR code takes you to our GitHub repo, and you can find the paper there as well. So thank you so much for listening and your time. I really appreciate the time to speak to you about this. Thanks so much.